6.2, apply properties of rational exponents. So let a and b be real numbers, let m and n be rational numbers. This one's called the product of powers because we're multiplying two powers together. So a to the m times a to the n, notice that the bases match, equals a to the m plus n. So if we have 5 to the 1/2 times 5 to the 3/2, that's the same as 5 to the 1/2 plus 3/2, which is 5 to the 4/2, or 5 squared, so 25. Okay, here we have power to a power. So we have 3 to the 5/2 raised to the second power, just like our definition here. So then we take our exponents and multiply them. We have a 2 in the denominator and a 2 not in the denominator, so those can cancel. So we get 3 to the 5th, which is 243. Here we have power of a product. So we're multiplying two things and then raising that product to a power. So we basically distribute this exponent out. We can only do that if it's multiplied though. We cannot do it if it's added or subtracted. So then we have, our example is 16 times 9 to the 1/2, which is the same as 16 to the 1/2 times 9 to the 1/2. 16 to the 1/2 is the square root of 16, which is 4. 9 to the 1/2 is the square root of 9, which is 3. 4 times 3 is 12. Next is negative exponents. So when we have a negative exponent, in order to make it positive, we can put it in the denominator of a fraction. So if we have 36 to the negative 1/2, to make that positive, we can put it in the denominator of a fraction. So 36 to the 1/2 is in the denominator, and 1 is our placeholder in the numerator. 36 to the 1/2 is the same as the square root of 36, which is 6, so we get 1/6. Next is zero exponent. Anytime we have an exponent of 0, the answer is 1. So, negative 5 to the 0 power is 1. 500 to the 0 power is 1. 1/2 to the 0 power is 1. Anything to the 0 power is 1. Okay, so now we have quotient of powers. So we have a power divided by a power, and we subtract our exponents there. So 4 to the 5/2 over 4 to the 1/2 is the same as 4 to the 5/2 minus 1/2, which is 4 to the 4/2, or 4 squared, so we get 16. The last one is power of a quotient. We're dividing and then raising to a power. And basically we can distribute that out Remember, we cannot distribute our exponent if it is added or subtracted, only if it is multiplied or divided. So 27 over 64 to the 1/3 is 27 to the 1/3 over 64 to the 1/3. So it's the cubed root of 27, which is 3, and the cubed root of 64 is 4. Okay, so here we have a product of powers. We have two things that we're multiplying together that are exponents. So we're going to add our exponents. Now, we have to get a common denominator in our fractions here. So 1/4 can stay 1/4. 1/2 is the same as 2/4. When we add those together, we get 3/4. We can't take the 4th root of 7, so we just leave it just like that. Right. Here we have a power of a product. So we can distribute this out because this is multiplying. So 6 to the 1/2 squared times 4 to the 1/3 squared. Now we have a power to a power. So we can multiply our exponents. So 1/2 times 2, 1/3 times 2. These 2's cancel, so we just get 6 to the first power, or 6. And then the 4 becomes 4 to the 2/3. And we can't simplify that anymore. So that is our answer. Okay, here we have a power of a product again. Move this up. So we can distribute this out because we have a multiplication sign here. So 4 to the 5th to the negative 1/5 times 3 to the 5th to the negative 1/5. We can multiply our exponents because we have a power to a power. Those cancel, we're left with negative 1 here. Those cancel, we're left with 1, or negative 1. So we have 4 to the negative 1 times 3 to the negative 1. Now we have negative exponents. So we can put 4 in the bottom of a fraction and 3 in the bottom of a fraction. So we get 1/4 times 1/3, which is 1/12. Now here we have a quotient of powers. So this 5 doesn't have an exponent, so we know it's a 1. And we have a quotient, so we're going to subtract our exponent. So 5 to the 1 minus 1/3. 1 is the same as 3/3. So if we subtract those, we get 2/3. We can't simplify that anymore, so we're done. Okay, this one, we have a quotient to a power. So the power of a quotient. So we can distribute this out because it's divided. So we get 42 to the third squared over 6 to the 1/3 squared, which will give me 42 to the 2/3 over 6 to the 2/3. Since we're taking power to a power, we can multiply these. Now, we have the same exponent in both cases, so we can use this property backwards and pull out our exponent. And then we can take 42 divided by 6, and we get 7 to the 2/3, and that we cannot simplify anymore. So we are done. Now, properties of radicals. First, we have the product property of radicals. So if we have a root of something times something, we can break that into two roots, both with the same index as the original, of those two things times each other. So if I have the fourth root of 16 times 81, that's the same as the fourth root of 16 times the fourth root of 81, which is 2 times 3, so we get 6. Okay, then the quotient property of radicals is very similar to the product property of radicals. If we have one root of a quotient, we can break that into the quotient of two radicals, both with the same index as the original. So the cubed root of 8 over 27 is the same as the cubed root of 8 over the cubed root of 27, which is 2 over 3. Okay, so let's go ahead and simplify these. So for these, we're using these properties backwards. So we have them separated. Let's go ahead and put them together. So this is the cubed root of 12 times 18, which is the cubed root of 216, or 6. Here we can put them together just like that. So the fourth root of 80 over 5. 80 over 5 is 16. So we get 2, and this index is even, so it's positive or negative 2. A radical with index n is in simplest form if the radicand has no perfect nth powers as factors and any denominator has been rationalized. Remember, a rationalized denominator means no radicals. Radical expressions with the same index and radicand are called like radicals. Basically like terms. Okay, so we are going to simplify completely. We're going to write it in simplest form. So we have an index of 3, so we're looking for any perfect cube that goes into that. I'm going to use some scratch paper here. Perfect cube, okay, is any power So any cube, so any number that has a perfect cubed root. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. So we are looking for any of these numbers that go in evenly to 135. And we end up getting that 27 times 5 is 135. So this is the same as 27 times 5. And then using the product power property of radicals, we can break this into two pieces. So the cubed root of 27 times the cubed root of 5. The cubed root of 27 is 3. And the cubed root of 5 stays the cubed root of 5. Okay, the fifth power one now. We want to get the fifth root out of the denominator. So, we are going to rewrite this as two separate things. Okay, so we have the fifth root of 7, just like here. Now, I'm going to factor 8. So 8 factors into 2 and 4, and 4 factors into 2 and 2. So I have 3 2's. So 8 is the same as 2 to the third. Now I need to get 5 2's. So I need to multiply by 2 squared. So I'm going to multiply the top and the bottom by the same thing. So I get the fifth root of 7 times the fifth root of 4 over the fifth root of 2 to the fifth, because we add our exponents. This cancels here. So we get the fifth root of 28 if I use my product property of radicals to combine those, all over 2. And we cannot simplify this because this is under a radical and this is not. So that is our answer for that one. Okay. Here we have the fourth root of 10, and here we have 7 fourth roots of 10. This is like 1 times the fourth root of 10. So we have 1 of those, and then 7 of those. So that makes a total of 8 fourth roots of 10. Here, we have kind of the same thing. So we have 8 to the 1/5 and 8 to the 1/5. So we have 2 of those, and then we have 10 of those. So that makes 12. 8 to the 1/5. And then here, these aren't the same, so we're going to have to simplify this one. So, again, we are looking for perfect cubes. So one of these numbers that goes into 54, and it happens to be 27 again. So 54 is the same as the cubed root of 27 times 2. So then we separate that, so the cubed root of 27 times the cubed root of 2 minus the cubed root of 2. The cubed root of 27 is 3. Cubed root of 2 minus the cubed root of 2. So we have 3 cubed roots of 2, and then we take away 1. This is essentially 1 cubed root of 2. So we get 2 cubed roots of 2. Okay, now, when n is odd, we cancel these out and just get x. For example, the 7th root of 5 to the 7th, we cancel those out and we just get 5. When we have the 7th root of negative 5 to the 7th, we just get negative 5. But if we have the nth root of x to the n when n is even, then our answer is the absolute value of x. So the 4th root of 3 to the 4th is just 3. And the 4th root of negative 3 to the 4th is also just 3 because we take the absolute value of our number. So again, we have a difference between when our index is odd and when it's even. So the cubed root of 64, because we can break this apart, cubed root of 64 times the cubed root of y to the 6th. The cubed root of 64 is 4. The cubed root of y to the 6th, we divide our powers here, so 6 divided by 3 is 2. Okay, we have a power of a product here, so we can distribute. Remember, we can't do that if we were adding or subtracting. So 27 to the 1/3, p to the 3rd to the 1/3, and q to the 12th to the 1/3. So 27 to the 1/3 is the cubed root of 27, or 3. Here our exponents multiply and cancel, so we just get a p. And here our exponents multiply, so we get q to the 4th, because it's 12/3, which simplifies to 4. Here we have a quotient, or a radical of a quotient here, so we can rewrite that as the 4th root of m to the 4th over the 4th root of n to the 8th. Again, we divide our exponent by our index, so 4 divided by 4 is just 1, so we just get m. 8 divided by 4 is 2, so we get m over n squared. Now, here is a little bit trickier because we have a 5 here. Okay, we cannot take the 5th root of 5, so that, or the 5th root of 4, so that 4 is going to stay under there. Now, 5 goes into 8 once, so we are going to put 1a out here, and there are 3 left over. So we're going to leave a to the 3rd under there. Then 5 goes into 14 twice, so I'm going to pull out b squared, and there are 4 left over, so I'm going to leave b to the 4th under the root, and then 5 goes into 5 once, so I pull out a c with nothing left over, so I don't leave any c's under the radical. So that is my answer there. On this one, we can rewrite it as the cubed root of x over the cubed root of y to the 8th. Now, 3 goes into 8 twice. So we get y squared on the outside. And then the cubed root of, we have 2 left over, so y squared. We need to get this radical out of the denominator. So I need another y to go here. So I'm going to multiply by the cubed root of y to the first, because when I multiply these together, I'll get 3. So the cubed root of y to the first. So I can combine these and say the cubed root of xy, because y to the first is just y. And then here I have y squared, and then the cubed root of y to the third, because I add my exponents here. This goes away, so I'm left with y squared times y. So xy over y to the third. This is under a radical, so I cannot cancel out that y. So that right there is my answer. Okay, so now this one, I have a 2 here. I can't take the cubed root of 2, so I'm going to leave that under the radical. But 3 goes into 5 once, so I'm going to pull out a z. And then I have 2 left over, so I leave a z squared in there. Minus, now 54 seems like a pretty big number to stay in there. So I'm going to list my perfect cubes again. So perfect cubes. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 64 is more than 54, so I can stop. Okay, I need to look and see, do any of these numbers go into 54 evenly? And yes, it's 27 again. So I can rewrite this. I'm going to rewrite it over here. So the cubed root of 54 is the same as the cubed root of 27 times the cubed root of 2. The cubed root of 27 is 3, and I'm left with the 2 inside the cubed root. So a 3 is going to come out of my cubed root here. My z is already out there. 3 does not go into 2, so I cannot take out any more z's from here. And I am left with 2 z squared left in here. Now I have the cubed root of 2z squared here, and the cubed root of 2z squared here. So I have like radicals. I have a z and a z outside, so 12z minus 3z is 9z cubed roots of 2z squared. Okay, so that's how you do those.